Welcome everyone. This is the last lecture of undergraduate seminar series for 2024. Today we have Gerlo speaking again, and he will tell us if he needs to update his eigenvalues or not, and why. Thank you.
Okay, hello everyone. Thank you for coming. So we've all been there. You know, we're bored at home. We open up Google. We type in funny cat videos, and we get a whole list of different pages, right? But has anyone actually wondered how that search algorithm works? Great, because that's why we're here today. So, you know, it seems reasonable to think that Google just counts the amount of occurrences of your keywords in your search in the pages, right? Just says, okay, well, this page has your keywords about 10,000 times, this one has it about 3 times, so the one is more relevant than the other, right? Now, this is actually called a text-based ranking system, which was used in the early 90s by you know, some people in the room who were born then. But obviously this wasn't super effective, because you could search up a word like internet and you just get a page with a bunch of Chinese and the word internet a couple of times. Or you could search up cats and just get the random cat lady's page that just says cats over and over and over and over again, instead of something a bit more relevant, you know, like let's say the Wikipedia page for cats. So what we need to do is we need to also consider the relevance of a page, the importance of a page, not just whether it has your keywords or not, right? Now, one of the most known and influential algorithms used is called the PageRank Algorithm, and it's used by Google. It was invented by Larry Page and Sergey Brin while they were still graduate students at Stanford, and it became an official Google trademark in 1998. Now, the main idea is the following. We say that the importance of a web page is judged by looking at the pages that link to it. So, say we have a page I. We create some page I with some topic, and on our page, we link to J. So we assume that if you link to a page, then that page is relevant to the topic, right? So here we just say that J is important. Beautiful handwriting. Now, if you have a bunch of different pages that link to J, so a bunch of different pages all linked to J, then obviously we say, okay, well then clearly there's a consensus that says that J is important. So we just say, okay, J is really important. And then lastly, we say that if we have some page, call it K, where K carries a lot of authority, right? Like, say K is Google itself, and K links to J, then we say that K transfers its authority to J, right? Right. So that's the main idea behind this PageRank algorithm. Now, we obviously need a way to express our network, to represent our network. So the way that we're going to do that is we're going to be using a bit of graph theory. We're going to say that our network is just a directed graph. Right. So say we have some graph, 1, 2, 3, 4. Now, these nodes or these vertices will represent the different web pages, right? So these are our web pages, are represented by the nodes. And now we said we consider the different pages that link to it, right? So different hyperlinks from one page to another. And we express these as edges, directed edges. So say, for example, we have one down like that, one across like that, one down like that, and like that. So in this case, there's a hyperlink from page 1 to page 3, a hyperlink from page 4 to page 3, 4 to 1, 1 to 2, 2 to 4. Right, so these represent our links. And then lastly, a bit of terminology that we need to know is just connected and strongly connected. So we say that a graph is connected when between any two vertices, there's a directed path either from the one to the other or from the other to the one. So in this case, this graph would be connected because, say, for example, from 3 to 2, there's a path from 2 to 3, so it's connected, right? So we can say this is connected. Now, the only difference between connected and strongly connected is that a graph is strongly connected if from any one vertex, there's a directed path to any other vertex. So in this case, this wouldn't be strongly connected because while there is a path connecting 3 and 2, there's no path from 3 to 2. But if we just add something like that, then it becomes strongly connected. Right, so a bit of important terminology, right? Now, for this lecture, we'll consider our own little mini internet, right? We will say that we have 4 pages. Page 1, 2, 3, and 4, with hyperlinks from 3 to 4, 1 to 3, 3 to 2, 2 to 4, 4 to 1, 1 to 4, 1 to 2, and 2 to 1. Right, so this is going to be our mini internet that we consider for the talk. Now, you'll notice that this one is strongly connected. Right, from any one vertex, there's a path to any other vertex. You're welcome to go check. It is strongly connected, right? Now, we get into the fun of it. When we look at these 4 pages, right, we're going to hazard a guess before we get into it. We say that the importance is based on the pages that link to it. Now, if we have a look at this graph, which would you guess is more important? Four, right? Because if you have a look, we see that 1 simply has 2 that links to it, 2 has 2, 4 has 3, and 3 has 1. So we hazard an initial guess and we say, okay, so we think 4 would probably be the most important, right? Now let's see if that's true. Now, since the importance of a web page is measured by its popularity, so to say, or the incoming links from other pages to it, right? We can view the importance of a page I as simply the probability that a random user on the internet will end up visiting page I. Right? So if they start some page and they click on a bunch of hyperlinks and move through the pages, we say that the importance of a page I is the probability that if they follow these hyperlinks, they will visit this page I. All right. Now, to represent this, we're going to be using some weights. We're going to go gymming. So how we do this is we assign weights to the directed edges. And we say, okay, well, let's say we start at page number 1, right? If we start at page number 1, there's 3 different hyperlinks that we can move to a different page with, right? So if we start at 1, then there's a probability of a third that someone uses this hyperlink, a probability of a third that someone uses this hyperlink, and a probability of a third that someone uses this hyperlink. Right? And then we go through and we do that for all the directed edges. We say that from 2, there's simply 2 edges, so a half and a half. From 3, there's also 2 edges, so a half and a half. And then from 4, there's only 1 edge, so that's just 1. Right. So now we assign weights to these different directed edges. Okay. Now, let's say, for argument's sake, that the user starts at page number 1. So we can express this as simply saying x0 is equal to 1, 0, 0, 0. Where now 1 is a probability vector. Now, a probability vector is just a vector whose entries sum up to 1, right? And we say that, okay, so the probability of being on page 1, in this case, is 100%, so that's 1. Page 2, 3, and 4 is 0, so that's just 0, right? For a more general case, we can say that x0 is equal to a quarter, a quarter, a quarter, and a quarter. Simply saying that the user can pick any one of the 4 pages to start with, but to make computations a bit easier, we'll just stick with this one to start with. Right. Now, the way we're going to model this user walking through our mini internet, clicking on different links, going from page to page to page, is we're going to use directed walks, right? And the way we do that is we're going to need a transition matrix. Now, the transition matrix we construct in the following way. We say that the first column represents the first page. Second column represents the second page, third column, fourth column, etc. Right? And then the entry in the first row represents the link linking to page 1, second row linking to page 2, third row linking to page 3, fourth row linking to page 4. So, if we start column 1, page 1, there's no link linking to page 1, so that's simply 0. If we start at page 1, there is a link to page 2 that has a weight of a third, so we just say that's a third. Then we keep going. We say from 1 to page 3 is a third. From 1 to page 4 is a third. And that completes the first column. Right, then we can go further and we say from 2 to 1 is a half. From 2 to 2 is 0. From 2 to 3 is 0. And from 2 to 4 is a half. From 3 to 1 is 0. From 3 to 2 is a half. From 3 to 3 is 0. From 3 to 4 is a half. And then from 4 to 1 is 1. And there's nothing else, so the rest is just 0. All right, so then this gives us our transition matrix. Now the way we use it is as follows. We say, okay, so let's say they started at page 1, right? And we have this initial vector 1, 0, 0, 0. So then after one step, we find x1 to be t times x0, which just gives us 0, a third, a third, a third. Right. So what this means is that if they started at page 1 and they clicked on only one hyperlink, then there's 0 chance that they're still on page 1. There's a third of a chance that they're on page 2, a third that they're on page 3, and a third that they're on page 4. Right. And then we can keep doing this to get, after 2 steps, x2 is equal to t times x1, which is just t times the t of x naught. So that's t squared of x naught, which is just a half, a sixth, 0, and a third. Right. So then similarly, after 2 steps, so starting at page 1 and clicking on 2 hyperlinks, there's half a chance that they're on page 1, sixth of a chance that they're on page 2, 0% chance that they're on page 3, and a third of a chance that they're on page 4. All right. Now using this same trick, we can go and generalize this to k steps. And we just see that xk would be given by t to the k times x naught. All right. Let me take a sip of water. It is very warm. Now, we can keep doing this, right? And we eventually get a sequence of these xk's. Now, what we hope eventually happens is that we reach some equilibrium, some vector q, such that tq is equal to q, right? Because the idea is then, this q is the eventual probability of them ending at some page. So then the ith entry of this q would be the probability of visiting page I, right? But this obviously begs a couple of questions. Does a q even exist? Does it depend on our choice of x0? And if the q does exist, can we guarantee that it would converge to this q? Well, here's where the theorems come in. So, the first theorem, better known as the Perron-Frobenius Theorem, which I am just going to abbreviate with PF, because that is too much to say every time, goes as follows. Let A be an n by n irreducible matrix. Then there is a positive number r called the Perron-Frobenius eigenvalue of A, such that r is an eigenvalue of A, and r is the spectral radius of A. All right? And then the second point is actually 4, but we're only going to be considering 2 for this case, says there exists a vector V called the Perron-Frobenius eigenvector corresponding to R such that all entries of V are positive. Now, just a bit of terminology. The spectral radius just refers to the eigenvalue with the greatest magnitude. So the absolute value of the eigenvalue is the one that's the largest, right? And you can go and look up the definition of irreducible. It's complicated. So we're just going to be using its characterization, saying that if we take a matrix and we replace all of its entries with a 1, and consider that to be an adjacency matrix, then the graph that that corresponds to would be a strongly connected graph. All right. Sorry? I don't believe we need it here. Yes, sorry. Replace all of the non-zero entries with 1. Yes. All right. Then we have a couple of other theorems. So theorem 2 says the following. If, in this case, A is positive, n by n matrix. So positive just meaning that all of its entries are positive real numbers, right? Where the entries in every column sum up to some value k. Then this k is our Perron-Frobenius eigenvalue. Okay. So of course, if it is the eigenvalue, then it's also the spectral radius. All right. And then the third theorem says, let A once again be positive, with spectral radius 1, and let V be any positive vector in Rn. Then the sequence V, AV, A squared V, converges to the Perron-Frobenius eigenvector of A or the zero vector. All right. Yes.
Just to be clear, the PF eigenvalue is by definition the largest one.
Yes, correct. All right. Now, we said that we need some equilibrium vector TQ equal to Q. Right? Now this corresponds to Q just being an eigenvector corresponding to the eigenvalue of 1. Right. So what this tells us is that if this T, if all of its columns sum up to the number of 1, then by theorem 2, 1 would be our PF eigenvalue. Right? Then by definition, 1 would also be our spectral radius, which means that the sequence will converge for any starting vector v. Right. So that's what we need to try and find, is see whether these columns of T sum up to the number of 1. Right. Now, these matrices whose columns sum up to 1 actually have a special name. They're called column stochastic matrices. By definition, column stochastic matrices are just square matrices with non-negative entries whose columns are probability vectors, right? Meaning their columns just sum up to 1. Now, if you have a look at our T, 0 plus a third plus a third plus a third is just 1, right? A half plus 0 plus 0 plus a half is just 1. 0 plus a half plus 0 plus a half is 1. 1, 0, 0, 0, just 1, right? So we see that indeed T, in this case, is a column stochastic matrix, right? Now, this isn't perchance. We have a fourth theorem that says for any strongly connected graph, the transition matrix will be column stochastic. Right. So that tracks. Our graph is strongly connected. T is column stochastic. Great. Right? And if we look at T and we replace all of the non-zero entries with a 1, you just get the transpose of the adjacency matrix of this graph. In the wise words of Dr. Wortel, if you don't believe me, it's homework. But what this means is that the graph corresponding to this adjacency matrix will still be strongly connected, right? So T is irreducible, which now means that we can reformulate our first theorem just a tiny bit for this specific case. And we say that if T is instead positive and column stochastic, meaning all of its columns sum up to 1, which everything follows, right? Then there exists a positive number 1, such that there exists a 1, yes, such that 1 is an eigenvalue of T, and 1 is the spectral radius of T, right? And then similarly, there exists some vector Q such that it corresponds to 1 and all the entries of Q are positive. Great. Okay. Because now we see that T satisfies all of this, right? So this sequence, Tk x naught for k equals 0 to infinity, this sequence will converge, right, to this vector Q. Now, the last little thing we need to consider is that we need this Q to be a probability vector, right? So all its entries need to sum up to 1. Now, this is never actually stated in the theorem. It just says positive entries. But since scalar multiples of eigenvectors are still eigenvectors, if need be, we can just multiply Q with a constant so that its entries sum up to 1. All right. Now, if we go and do this, and we go and keep multiplying T, and keep multiplying T, and keep multiplying T, we eventually find Q to be 0.387, 0.194, 0.129, and 0.290. And this gives us our PageRank vector. So what this means is that our rank is given by, if I can spell page, page 1, followed by page 4, then page 2, and then page 3. But that's strange. I thought we said page 4 is the most important. Well, this is due to this last little bit here, right? Because the idea here is that 4 is incredibly important. But 4 only has one hyperlink going to a different page, specifically the one linking to 1, which means that 4 transfers all of its importance to page number 1. Another way to think about it is that if someone ends up at page 4, which they very likely will, they can't go anywhere else but page number 1. Right. So in our system, we would first list page number 1, then page number 4, page number 2, then page number 3. But there's a little problem, just a tiny problem, right? Because this only holds for strongly connected graphs. So what happens when it's not strongly connected? So what if we have 1, 2, and 3, little something like that, right? And the internet has millions and millions of pages, so it's likely to think that the graph won't be strongly connected. Well, in this case, using the same method, we see that our transition matrix is given by 0, 0, 1, 0, 0, 1, 0, 0, 0. So if we decide to do the general case and we say, okay, let x0 be equal to a third, a third, a third, well, then we find x1 to be 0, 0, 2 over 3, which is already an issue, right? But hey, for argument's sake, let's see what happens next, right? Then we get x2 Now, surely this can't be right, because clearly page 3 has some importance, but according to this, none of them have a rank. Okay, so what happens if it's not even connected at all? Let's take it even further. Erase this now. So what if you have something like this? Links between them. Links between them. Right, so that's not even connected at all. Well, then our transition matrix looks a little something like this. 0, 1, 1, 2, 3, 1, 0, 2, 3, 0, 0, 0. Looks a little something like that, right? Well, then we get these two vectors. Which are both eigenvalues corresponding to eigenvectors corresponding to the eigenvalue of lambda equals to 1. So what do we do with this? Well, luckily for us, Page and Bryn are very clever, and they accounted for this, right? So what we do is the following. We say, we fix some constant p between 0 and 1. Right? Now, the value usually used for P is about 0.15. I'll tell you what P is in a second. And then we define a matrix M to be 1 minus P times T, where T is our transition matrix, right? Plus P times B, where now B is just 1 over n times 1, 1, 1, 1, 1, 1, that matrix. Now, this matrix M is usually referred to as the PageRank matrix, or simply the Google matrix. Now, P is a little bit of a probability that they introduce. Because, you know, what we considered is starting at a page and clicking on hyperlinks and exploring and going through. But it happens that they click on a page, nah, I don't want to look at this one, they just jump to another one, right? So now P represents the probability that this user, this surfer, just quits on the page that they're on and goes to another page, teleports to some other page, right? So what this means is that every page has at least a probability of 1 over n, where n is the number of pages, to be chosen, right? Whether there's a hyperlink between them or not, there's at least a probability of 1 over n.
P over n.
At least 1 over n. But in this case, P over n. Because for a node like 3, which has no outgoing edges, there's a probability of P over n to go to any other node. Right. And then our PageRank vector, which we denoted with Q in this case, for this whatever web graph looks like, and a transition matrix T, and some damping factor P, right, is just the unique probabilistic eigenvector of this M corresponding to the eigenvalue of 1. And using this, no matter what graph you throw at us, we can find some rank for the pages and give you all the search results you could ever want. And that's how Google works.